When you walk into a classroom filled with chalk dust, tired students, and a long blackboard that seems to stretch into the next county, you expect a certain kind of lecture. Maybe you think you will hear a tidy sequence of facts, a definition or two, and then some smooth derivation that behaves itself from start to finish. But real physics almost never behaves itself. If it did, we could all have gone home 100 years ago. Instead, physics is more like a stubborn puzzle that keeps throwing new pieces onto the table after you think you finished it. And in the middle of that pile of pieces sits a question that bothered many of us for a long time. Why does the quantum world look so strange? And why did the old equations seem to hide more than they revealed? Imagine light moving from one place to another. You might first think of waves on a pond spreading out in smooth circular ripples. Then someone tells you that light also behaves like a stream of tiny particles. So far, so good, if you are willing to accept that nature sometimes picks random costumes. But the real trouble begins when you send a single particle of light through two slits and find that it produces an interference pattern, something you would usually expect from waves. It is as if nature refuses to decide whether it is a wave or a particle. This was the mystery that puzzled almost every physicist who worked on quantum theory in the first half of the 20th century. Back then, quantum mechanics came in two flavors. One was the wave picture that Schrödinger invented, smooth and graceful and full of beautiful equations. The other was Heisenberg's matrix picture, which looked like a giant bookkeeping exercise with numbers stacked in mysterious arrays. Dirac, who loved elegance more than almost anyone, tried to unite the two, and he did a pretty good job. But when physicists tried to use these tools to understand how particles like electrons and photons interact, especially when they come close together, the calculations started to develop serious problems. Some of these problems were so big that the equations blew up to infinity. And while infinity might be acceptable in poetry, it is not very helpful when you are trying to design a theory that predicts measurable numbers. You might wonder why anyone kept going if the equations seemed so simple. The reason is simple. They worked well enough in many cases to give results that matched experiments. But nobody liked the idea of patching the theory with tricks that looked more like bookkeeping than real science. It felt as though we were sweeping dirt under the rug, hoping no one would notice the large mound growing in the corner. Now picture someone who cannot stand a messy desk, let alone a messy equation. Someone who dislikes hand-waving explanations and prefers to see how nature behaves in a straightforward, almost playful way. That attitude is where the spark of a new idea often comes from. Instead of accepting the traditional formulas, the idea was to look at the problem with fresh eyes, to ask whether there might be a simpler story behind all the complexity. And that led to a strange thought. What if a particle does not take a single path when traveling from one point to another? What if it takes every possible path? This might sound like a fairy tale, but hold on. When we say every possible path, we mean it in a mathematical sense. Consider a dog trying to run from its owner to a thrown stick. The dog might not pick the shortest route. It might zigzag, sniff a few interesting spots, circle a tree, and then dash forward. If you tried to write an equation for that, you would give up quickly. But in the quantum world, something surprising happened. A particle seems to explore every zigzag, every loop, every wild detour you can imagine. Then, after adding up the effects of all these possibilities, a clear pattern emerges. To make this idea precise, we need a little calculus. Not the usual calculus of slopes and areas, but something deep. Picture the concept of action, which is the integral of energy over time. In classical physics, nature often picks the path that minimizes this action. It is a bit like how a traveler might choose the cheapest flight rather than checking every option. But the quantum world seems to do the opposite. It checks every option. Every path contributes to the final outcome, but not equally. Some paths reinforce each other. Others cancel out, much like noise-canceling headphones remove unwanted sound. The mathematics behind this idea involves something called a path integral. Instead of summing numbers, you sum whole functions representing entire paths. If that sounds intimidating, think of it this way. You assign a tiny arrow called a phase to each possible path. Then you add the arrows. Paths that make physical sense line up and point in the same direction. Wild paths twist around and cancel each other out. The result is a clear prediction for where a particle is likely to end up. This may seem like advanced calculus, but the heart of it is simple. Nature tries everything, and then the messy attempts wash out, leaving the best path as the one most likely to appear in the classical limit. At this point in the story, imagine a blackboard full of chalk lines. We start with a single point where an electron begins, then we draw another point where it ends. Between them we sketch hundreds of crooked lines. It looks chaotic, but as each line gets its phase assigned and summed, order emerges. That order is quantum mechanics written in a new language, one that does not hide behind abstract symbols, but uses pictures and clear reasoning. Now let's walk into a moment when a new thought begins to replace an old one. The traditional equations were powerful but felt opaque. They did not show what was happening. They were like reading a recipe written in a language you barely understand and hoping the cake comes out right. But imagine replacing the recipe with a simple set of diagrams. Each diagram shows exactly what particles do when they interact. There is a straight line for an electron, a wiggly line for a photon, and a point where they meet. These diagrams are not doodles. Each one stands for a mathematical expression. If you can draw it, you can calculate it. Why would drawing a picture make physics easier? Because pictures can reveal relationships that equations hide. Think of a subway map. It is not drawn to scale, but it tells you how one station connects to another. You do not need to memorize long lists of numbers to understand where to go. In the same way, a diagram showing how two electrons interact through a photon exchange reveals the structure of the calculation. To appreciate how radical this was, we need to step back to the days when physicists were wrestling with infinity. Every calculation seemed to produce giant terms that made no physical sense. Even the best theorists struggled to tame these beasts. The path integral and the diagrams built from it did something remarkable. They turned the problem inside out. Instead of hiding the infinities, they exposed where they came from and how to control them. The approach treated the calculations more democratically. Instead of trying to force the theory to behave, it let the underlying structure speak for itself. Why does this matter for someone who is not a physicist? Because it shows that the universe can often be understood with simple ideas wrapped in advanced mathematics. You do not need to follow the heavy math to feel the meaning. If you have ever stood in front of a noisy crowd and tried to pick out a friend's voice, you have already experienced how constructive and destructive interference works. If you have ever watched many people trying to choose a restaurant together, you know how combined decisions average out. The quantum world works through these same patterns, only with far more precision. The next key idea is that classical physics, the physics of falling apples and orbiting planets, is not wrong, it is just incomplete. When you zoom out to large scales, all those crazy quantum paths cancel until only the smooth classical path remains visible. It is like looking at a painting from across the room. Up close you see wild brushstrokes pointing in every direction. But from far away, the strokes merge into a clear scene. Classical mechanics is the distant view of quantum mechanics. To express this idea mathematically, you often write an exponential with the action divided by a tiny constant known as Planck's constant. This exponential creates oscillation. When the action varies a lot from one path to another, the oscillations cancel. When the action changes very little, the oscillations line up. That is why classical paths dominate. You can think of it like tuning a guitar. If the string is slightly off, the sound wobbles and fades. But when tuned just right, the vibration stays strong and pure. Classical physics is the strong, pure note that rings out from the many possibilities underneath. This approach does something beautiful. It unifies the strange quantum behavior and the familiar classical behavior with a single principle. Instead of having two separate theories stitched together, you get one continuous story. It is the same story whether you look at atoms or baseballs, just written in different scale. But breakthroughs rarely come from equations alone. They come from a certain attitude toward the world. Curiosity helps, doubt helps even more. One must be willing to question ideas that everyone else seems comfortable with. The quantum equations worked, but only in a narrow sense. They predicted results, yes, but they did not explain why nature chose those results. The new picture summed paths and diagrams offered something the old picture could not: transparency. To illustrate how these ideas work in practice, imagine a simple event. An electron travels through empty space. In the classical picture, nothing much happens. It marches forward like a soldier, But the quantum picture says something else. The electron is busy. It is constantly wiggling, jittering, and exchanging virtual photons with the vacuum. These virtual particles pop in and out of existence. Though they cannot be directly observed, their effects appear in measurable ways, such as the electron's magnetic moment. A diagram draws this clearly. A line for the electron, loops attached to it for its virtual interaction. These loops used to be the source of horrible infinities, but once you draw them and analyze them carefully, you see how they fit together. The key idea is not to ignore the infinities, but to redefine the quantities in a way that strips out the non-physical pieces. This leads to a process we now call renormalization, though we do not need the name to appreciate the idea. The trick is simple in spirit: isolate what is real and measurable, and drop what is not. The breakthrough brought order to chaos. Suddenly, the calculations that once seemed impossible became manageable. Physicists could compute the behavior of particles interacting with light to astonishing accuracy. Experiments confirmed these predictions with precision so high that it almost felt unfair. It was like predicting the width of a football field to the thickness of a human hair. But the diagrams were more than a computational tool. They were a new way of thinking. They showed that complex interactions are built from simple pieces. You can take any event, break it into steps, draw each step, and then compute its contribution. This modular approach is similar to how engineers design bridges or how musicians build chords. You take small, understandable parts and combine them in structured ways. As these ideas grew, they changed everything in quantum physics. They made it possible to handle problems that had resisted progress for years. They opened doors to new theories, new predictions, and new insights about the deep workings of nature. And all of it began with a willingness to question tradition, to replace abstract equations with pictures, and to let nature reveal her patterns through clarity and simplicity. The heart of this approach is that the universe is not trying to confuse. It is we who choose complicated explanations when simpler ones will do. When you strip the world down to essentials, you find that particles interact through basic rules. They exchange quanta, follow probabilities, and add amplitude. If the picture looks messy, that is only because we are standing too close to it, and so the story of quantum physics changed. What once looked like a mysterious set of equations became a vivid landscape of paths, diagrams, and patterns that even a careful thinker with patience could appreciate. Mathematics did not disappear, far from it, but it became a tool rather than a barrier. It became a language that helped reveal the underlying simplicity of nature. What began as a strange idea that particles explore every path turned into a full framework that rebuilt quantum theory from the ground up. It opened a way to deeper insights, cleaner calculations, and a profound sense that nature might be far simpler than the first pioneers of quantum physics dared to imagine. There is a moment in any field of science when ideas that once looked harmless decide to misbehave. In quantum physics, this moment came when people started applying the theory to interactions between electrons and photons. These interactions should have been easy to describe with the equations available at the time, yet the results blew up into infinite value. One could calculate the energy shift of an electron, do every step correctly, and still end up with an answer that made no sense. It was like trying to measure the temperature of ice and getting the heat of the sun. Something was deeply flawed, not with the concept of quantum behavior itself, but with the way the theory tried to express it. Physicists are practical people in many ways. When faced with infinities they could not remove, some of them simply erased the bad parts of the calculation and kept the good parts, much like trimming burnt edges off a cake while hoping the inside still tastes fine. But trimming is not a theory, it is an apology for not having one. The challenge was to find a method that would produce the right answers without hiding the problems. The world deserved a theory built on clarity, not patches. This is where a new viewpoint helped more than expected. The idea that a particle takes every possible path gave a fresh way to look at the old problem. Instead of fighting the infinities inside the equations, the new approach showed how they were born. When you sum over all possible paths, some paths correspond to events that happen at extremely short distances or extremely high energies. These extreme paths, though essential to the mathematical framework, also introduce contributions that balloon into infinity. The trick is to handle them consistently, not selectively. And once you see how they originate, you can learn how to treat them without breaking the structure of the theory.
This perspective became clearer when diagrams entered the scene. A diagram is a small story about how particles interact. One line travels forward, another line joins or leaves it, and a wiggly line expresses a photon's role in the exchange. Instead of looking at equations that stretch across pages, you look at one picture. That picture tells you what integral you need to compute. It also tells you where infinities might appear. If a line loops back onto itself, if particles interact at a single point in a very tight way, or if two lines approach each other too closely, you know the calculation might produce an infinite term. But knowing where the trouble starts is half the battle. When a loop appears in a diagram, it tells you something physical. It does not say that particles literally spin in a loop. What it tells you is that the particle interacts with the vacuum, with fleeting disturbances that exist even in empty space. This interaction shifts the particle's properties. It changes its mass. It alters its charge. It makes a tiny correction that can be measured. And when these corrections are finally matched with experiments, the agreement is astonishing. The theory, once cleaned of its infinities using careful rules, gives predictions that match nature to many decimal places. But achieving that agreement requires a systematic way to subtract what does not belong. This cleaning process is often called renormalization, though the word is less important than the idea behind it. Imagine that you are trying to weigh a flea while holding it on a large pillow. If you place the pillow on a scale, the reading will be huge, but the size of the pillow does not interest you. What matters is the little difference between the pillow alone and the pillow with a flea on it. If you subtract the background weight correctly, you can discover the flea's weight. Nature forces a similar approach when dealing with quantum fields. The vacuum has a background weight, a set of contributions that always appear whether you observe them or not. You do not eliminate them by cheating. You subtract them by comparing the real physical quantity. This method, however strange it seems at first, produces results that match experiments with incredible precision. These diagrams did more than solve technical problems. They made quantum physics intuitive in a new way. When you look at a diagram, you see time flowing from left to right. You see an electron emit a photon, or a photon turning into an electron and positron pair for a brief moment. You see interactions as events rather than symbols, and behind each line there is a mathematical rule that tells you how to compute its contribution. The beauty of this is not only that it works, but that it shows how the universe can be described by simple building blocks assembled in different ways. As more diagrams were drawn, patterns emerged. Some diagrams were easy to compute. Others involved complicated integrals that stretched into the world of advanced calculus. These integrals often required changing variables, rotating axes in imaginary directions, or slicing infinite sums into manageable pieces. But even the hardest integrals shared a structure. They all followed the same rules. Each diagram was like a note in a larger musical score, contributing to a grand composition that described the behavior of fields and particles. One of the greatest triumphs of this method came when it was applied to a small, odd effect seen in hydrogen atoms. A tiny shift in the energy levels had been detected with high precision. Traditional theory could not explain it, but calculations made with diagrams predicted almost exactly the same shift. This agreement showed that the picture was not a clever trick. It was a true reflection of nature's behavior. When a set of ideas predict a subtle phenomenon with remarkable accuracy, scientists begin to trust them in deeper ways. The diagrams also taught an important lesson about simplicity. When facing a difficult problem, many physicists used to write down long chains of equations, hoping the correct answer would emerge if they followed the algebra far enough. But starting with a picture forces you to understand the structure before you attempt the calculation. It is like assembling a puzzle by looking at the image on the box, rather than dumping the pieces out blindly. You know what you are aiming for. You know the story behind the math. This clarity is not just a teaching tool, it changes how you think. When you try to solve a problem using diagrams, you stop worrying about arbitrary definitions or bookkeeping devices. You focus on physical processes, particles moving, exchanging energy, vibrating in field. You see how the whole universe can be described in terms of local interactions, simple events that add up to rich patterns. The sums involved in these calculations use advanced calculus, but the ideas can be understood without digging through every formula. When two particles interact each possible way, they can exchange a photon, contributes a tiny amount to the overall probability. Some paths involve simple exchanges, others involve complicated ones, with loops and twists. The total behavior is the sum of all possibility. These sums are written as integrals that extend over continuous spaces of variables, positions, momenta, energy. When an integral becomes too large in certain regions, you learn how to regularize it, trimming the problematic parts in a consistent way, then combining them back into a finite result. This approach respects the structure of the theory and does not alter the physics. Instead, it clarifies. With this viewpoint, quantum physics no longer seems mysterious. Particles are not magical. They are excitations of fields, vibrating in specific ways. A field can create or absorb particles. A particle can change direction when the field around it shifts. Even the vacuum is alive with subtle fluctuations. The universe becomes a dynamic system where nothing is ever perfectly still. Everything interacts, even when you think nothing is happening. This new understanding led to a broader perspective. Physics became a study not of isolated particles, but of fields spread across space and time. Each field has its own properties and excitations. The electron field produces electrons. The electron field produces photons. Interactions between fields are described by diagrams that show how one excitation influences another. This framework is known as quantum field theory. It is the foundation on which modern particle physics stands. These ideas changed how experiments were interpreted. When a particle collider smashes particles together, the interactions that follow can be drawn as diagrams. The diagrams predict how often certain events occur. They tell you what particles might emerge from the collision. They give a blueprint for understanding the patterns seen in detectors. The fact that so many predictions match experimental outcomes so well is strong evidence that the framework is correct. Of course, no theory is perfect. There are still unsolved problems in physics. Gravity does not fit neatly into the same framework, and the behavior of the universe at extreme energies still puzzles us. But the methods developed through this approach form the most accurate and successful theory ever created. They show that even when the universe looks complicated, its rules can be described in clear, almost playful ways. As we look back at this journey, one theme becomes clear: nature rewards those who pursue simplicity. The old equations were not wrong, but they hid the structure behind layers of formalism. When a new way of looking at the problem appeared, one based on paths, diagrams, and simple processes, the underlying order came into view. It is like cleaning a fogged window and finally seeing the landscape outside. The world did not become simpler, we just learned to see it better. Another lesson is that questions matter more than answers. Asking why the old calculations felt clumsy led to a new approach that reshaped physics. Asking how particles behave at small distances led to the discovery of paths and diagrams. Asking how to handle infinities led to consistent methods for removing them without breaking the theory. Science advances because someone refuses to accept that things must remain the way they are. Curiosity also plays a central role. When you ask how nature works, you should not be satisfied with a half explanation. You should push until the idea becomes clear enough that even a child could grasp it. If you cannot explain a concept simply, you might not truly understand. The effort to simplify forces you to confront hidden assumptions. It forces you to think more clearly, and in physics, clear thinking is more valuable than any particular equation. This approach does not belittle advanced mathematics. Instead, it celebrates it. Advanced calculus becomes a bridge between intuition and precision. It takes simple ideas and makes them exact. For example, the idea that all paths contribute becomes meaningful only because integrals allow you to add up infinite contributions in a structured way. When you compute these integrals, you learn how different paths interfere. You see how classical behavior emerges when the contributions from wild paths cancel out. Math turns the poetry of nature into measurable predictions. Consider the way a diagram tells a story. A single straight line describes an electron traveling through space. A wiggly line describes a photon. A vertex where they meet shows an interaction. Add loops, and you describe corrections from the vacuum. Add more lines, and you describe more complex events. Each diagram is not just a picture, it is a map of reality at the smallest scales. If you could zoom in on the world far beyond what microscopes can reach, these diagrams would reflect what you see, not literally as pictures, but as the underlying structure of interaction. Once you appreciate this, you begin to see how powerful the approach is. It explains why electrons repel each other, why atoms hold together, why materials behave the way they do. It predicts subtle shifts, rare events, and complicated patterns. It connects the small with the large, the simple with the complex. The success of this approach does not rest only on its conceptual beauty. Its power lies in its ability to make precise predictions. When we measure the magnetic property of the electron, for example, the theoretical prediction and the experimental value match to an accuracy of more than 10 decimal places. It is hard to find any other area of science where theory and experiment agree so well. This kind of precision gives confidence that the approach captures something fundamental about the universe. Through all of this, the spirit of exploration remains essential. Even when a theory works, you should not stop asking questions. You should test its limits, explore its failures, and seek new ways to improve it. Physics thrives on doubt. Certainty is the end of imagination. If you believe a theory explains everything, you stop looking for the cracks. But it is in those cracks that new discoveries hide. The ideas developed in this story form the backbone of much of modern physics, but they also carry lessons that reach beyond science. They remind us that clarity is worth chasing, that complexity often hides simple roots, and that pictures can reveal truths that equations sometimes obscure. They show that the world is understandable, not because it is simple, but because simple principles lie beneath its surface. And finally, they encourage a certain humility. The universe does not owe us clarity. It does not reveal its secrets easily, but with patience, curiosity, and a willingness to rethink old ideas, we can uncover patterns that once seemed impossible to understand. The journey is never finished. Every insight opens doors to new questions, and with each new question, the adventure continues.